Well, hello, good morning, good evening, good afternoon, depending on whichever part of the world you're joining from. My name is Mudit, and with me I have Claire, who's the Chief Operating Officer and co-founder of Pathway. I'm speaking this. Let me quickly go and check
Well, hello,
if
good
we are
morning,
live across
good evening,
platforms.
good afternoon, depending on whichever part of the world you're
Oops, I
joining
can hear
from.
myself, so we're definitely live on YouTube. I'll go and check across other platforms as well. Okay. Um, Let me check on LinkedIn as well if you're live. Ta-da. Yeah, we're live on LinkedIn as well. So, well, thanks everyone for joining in. Hi, Claire. Thanks for joining the call. And we have Vijay in the background for those of you who's wondering where is the main speaker. So, he's pretty much there. Thanks, Claire, for joining the call.
Yeah, thanks, Mudit. Thanks for the organization. Thanks, Vijay, for agreeing to being the keynote speaker today.
Yeah, definitely all kudos to him. To give a quick context for the ones who are, when we go for these streams, we always see there is a section of audience who doesn't know about, let's say, Pathway or our partners, let's say IIT Guwahati in this case, or probably they are new to the concept of the boot camp that we're running. So, a quick introduction in case you're not a part of the boot camp so far. So, this particular keynote session is the main keynote session that we are hosting as a part of our ongoing boot camp at IIT Guwahati. This is in partnership with Consulting and Analytics Club at IIT Guwahati, and they are one of the organizations under the technical board, which are responsible for preparing students for jobs in analytics, AI, consulting, etc. And they pretty much operate across India, but their base is certainly IIT Guwahati, which is one of the premier engineering institutions in India. And Pathway, I think Claire, if you could give a quick introduction of what Pathway is, what it does, that will be great for the audience.
Yeah, so Pathway is the easiest and fastest event stream processing framework. For the context, we are seeing that event-driven architectures are everywhere in every company, every industry. So we have this proliferation of real-time streaming data and event-driven architectures, and an increasing use of advanced analytics, ML, and AI, which are topics we will tackle today. So we see also that Gen AI is a must for companies to ensure they keep their competitive edge. They are completely transforming the technology stacks. Um, AI in enterprise relies on access to fresh data. We see data products that are combining multiple data sources. And there are a lot of trends that we're seeing on the market, and that's basically where at the crossroads of AI and live data that creates some unique challenges, and we're happy to solve them.
Okay, thanks. Thanks for that description. For those who would like to know more about Pathway, the website is pretty simple, pathway.com. You can go and read more about it. Um, and with that, let me do a quick introduction of this session. The session, as you can quickly see on LinkedIn, if you're joining there, or on YouTube, wherever you're watching it, it's around advances in computer vision, and where we'll try to understand the journey of moving from convolutional nets to spectral transformers and vision transformers. It's something that Vijay, who is our keynote speaker for today, he has worked quite extensively on. Talking about the bootcamp, by the way, I missed to do that. The bootcamp is an initiative where we try to. It's a non-commercial initiative where we try to educate people around generative AI, around large language models, around retrieval augmented generation. And given the current scope and the ecosystem around AI, given the entire surge in interest around multimodality and vision transformers, this session became more imperative in a way and came at just the right time. So if you're somewhere who are trying to understand this particular spectrum and see how it integrates well, how has the transition been from traditional pre-trained transformers to vision transformers, and their role, and the role of spectral transformers. So I think this session will be a good asset for you to look at. The format of this session is that after this quick introduction, there will be a presentation by Vijay. It's a technical session, so you will definitely have a lot of actionable learnings that you can go and work on. You'll also have access to a few links that we'll be sharing on the comments as Vijay is presenting them, like they're there in the presentation. So in case you struggle to type it in, we'll send it out. So just take along for you to ask questions. This is an interactive session, so there's some latency when we stream live. So when you ask a question, we may not be able to answer it right then and there. The format for that reason will be like you can simply put your questions, we'll curate the relevant ones and put them across to Vijay towards the end of the session. Without any further ado, let me give a quick introduction of Vijay and I'll bring him aboard. So Vijay is, by the way, a senior director, an ML research leader at Microsoft. He has done some amazing work at Microsoft, published a lot of patents. He also presented his work at NeurIPS quite recently. And beyond that, he has also led teams at Walmart and a ton of other great companies, which includes Oracle, Cognizant, and more. So thanks a lot, Vijay, for being here. And interestingly, for those of you who come from academia, Vijay is also an academician. Like, I mean, in the sense, he has done his PhD from IIT Madras, and then he did his postdoc from EPFL. So thanks, Vijay, for being on this session and sharing your time, your learnings with the community at IIT Guwahati and beyond.
Thanks, Mudit. Thanks for the intro. So I can go ahead right now. Okay.
Yeah, certainly.
You can see my screen, right?
Yes.
Okay, I'll go into presentation mode and we're all set. All right, so thanks and welcome to the session, folks. So the idea is to talk about some of the recent advances in computer vision. So what I had planned is to, for example, go from the traditional convolutional networks, which used to form the core of computer vision few years back, and then go all the way to vision transformers, and talk about all the recent ones, including the spectral transformers. So that's the intent, and in that process we'll also cover some of our own work, right, where we had published in NeurIPS in 23. So we'll cover some of that as well in the session. Cool. Yeah. So as you can see, right, we'll start with an introduction to computer vision. See, the intent is to, of course, it has a long history, and not so easy to capture in a short time frame. But I have made an attempt to capture some history of the CV. See, it is in some sense a clouded history, right? Because it's clouded by my own biases. But so that's what you will get, right? You will get a quick intro to computer vision and how convolutional networks used to form the backbone for computer vision, and then the advent of the vision transformer, and what kind of improvements were made to vision transformers for computer vision, and some of that we will see. And then we will go on to the scattering vision transformer, which is our NeurIPS work, and a little bit on the future work as well, right? Since I'm talking to a lot of people from academia, I put in some work, right, which can there. So without much ado, right, I'll get into the core of the content. So see, like I said, right, there is a lot of history, right, behind the field of computer vision, and one of the oldest is the paper from Hubel and Wiesel, which is they ran experiments and by showing different slides, right, to a cat, and mapping the brain of the cat to actually understand which part, right, of the brain gets activated by what kind of visual input and things like that. So one of the first ones to kind of experiment, right, with the machine vision, right, but through the eyes of the cat. And then you had, of course, the famous PhD thesis from Roberts, which actually was on machine perception of three-dimensional solids. So what he did was to take photographs of 2D solids and then reconstruct the 3D image from those photographs, and able to produce 3D images, right? And in much more greater detail, right, compared to the photographs. So that was the seminal work, this doctoral thesis. And of course, he, however, was not in machine vision field for a long time, but became one of the founders of the DARPA's internet project and all that. So, and of course, the following paper, right, which was again a seminal one, was by David Marr, and his paper was one of the first to talk about a hierarchical approach to computer vision. See, we keep talking about how the computer vision field is inspired by how humans perceive vision, and how humans perceive the world around them, right? So where the first we kind of look at edges and boundaries, and then try and understand more depth information, and right, and then piece together the overall 3D model, right, including the surface and volumetric primitives. So he gave a similar approach to machine vision, and which was one of the seminal papers, right, by David Marr. And of course, around this time, which was in the 70s, the first paper came out, right, which was the neurocognitron, and which was in some sense the earliest pattern recognizer, right, for images. So this was probably the first deep neural net, right, in a very literal sense, right? One of the seminal works in that space, where he had built a series of layers, and each layer had some set of neurons connected to other layers in some way, right? Some simplistic manner, but at least the initial the basis for modern deep neural nets is this neurocognitron paper by Fukushima, right? And of course, the seminal work also came from Jan LeCun's team. Of course, he is right now the AI lead at Facebook. He leads the AI for Facebook, and one of the prominent researchers in the AI space. So his first work, of course, LeCun and Bengio, their work was on what's called as LeNet. Of course, the coming from LeCun's network essentially, but yeah, the LeNet was the one of the first to be able to recognize handwritten characters, and this was able to give a good performance. And this was the first convolutional network, right, in the modern form. So the neurocognitron was a precursor to the modern convolutional nets. The LeNet was one of the first convolutional nets, and which gave good performance on handwritten characters, and also, right, the data set was also produced, which became useful. See, one of the main advantages, right, of having the data sets is that many people start building things, and they're able to train different kinds of networks on that data set, and so a lot of advances become possible once the data set becomes available. So this was also a main thing behind this paper. And then of course we can look at the very briefly, right, on how a convolutional net actually works. So the typical ways that the we have a window operator, right, which is the convolutional operator. So that is moving here, right? You can see that it's moving across the whole matrix, right, which is the input matrix, and it performs a convolutional operation, right, on the input. And then of course you have further operations, including the ReLU function, which gives the output to a pooling system, which is a max pooling operation. And then you will see that of course, there will be multiple layers of convolution, ReLU, and max pooling. So these layers get repeated number of times. So that becomes like a one layer of the convolutional network, and then you repeat that layer multiple times, typically 12 times, or it goes and it could be much larger. It could be as large as thousands in its current form. But then, yeah, initially, right, they did start with 12 and 24 and all that. Finally, you will have the fully connected layer, and before that, you will of course flatten the image, and the fully connected layer is followed by a softmax layer, which will do for example, the image classification, right? So this is how a typical CNN works. And of course, there were several adaptations of the same to make it work on other data. And for example, how does it work on sentences and NLP and all of that? But we will kind of stick to the image field for today. Sorry. so the see, one of the seminal works, right, in this space was this paper, right, from Hinton and his group. And you can see, right, Sutskever and Krzyzewski are all authors, right? This was famously called AlexNet. And see, this was one of the first to win the ImageNet. They had the competition, right? And this was the winner in 2012 of that large-scale classification competition. And since then, right, CNN's the convolutional nets became quite popular. Since the advent of this paper, right, from Hinton and his group, CNNs became popular, and every year, right, this ImageNet challenge was actually won by different forms of convolutional nets, and for a number of years, you could see that there are so many layers. We talked about it could be number of layers, right? There are 192 layers, and so this is of course the key was, see, while we saw that the convolutional nets were there much before, right, and the even the neurocognitron was one of the precursors to the convnets, right? What changed, and why was it able to get good results in 2012? See, this is because of course the implementation was on GPUs, and that became a significant thing, because earlier, prior to 2012, it took pretty long time for training any of these CNNs, and consequently, right, it took too much effort, too much computation effort to be able to train it and get any meaningful results out of these convnets. But because they were able to implement it on GPUs, they could train in a few hours the CNN, and able to show that, right, it gets about 16% error on the ImageNet data. So that was the AlexNet paper in 2012. And so with that, what we will do is quickly go to the world of transformers. See, just to introduce the concept of self-attention, which forms the basis of transformers, I'm delving into NLP realm, but we will come back to the realm of computer vision shortly. So if you see the the self-attention operation, right, it kind of, see, inspired by human vision. See, the thing is, human vision, right, in some sense, see, once we look at a scene, right, we tend to figure out very quickly where attention needs to be given, and which are the important parts of the image. And the human perception is very quick to figure out that and go to the important parts of the image. Whereas this becomes very hard in the case of machine vision, right? This is actually the hardest part. So this was what was solved by some of these attention nets, as they are called, right? Attention networks. And one of the variants of attention networks is the self-attention network that we are looking at in the screen, where see, every word is associated with every other word, and they see how important all the other words are for this particular word, and that is the attention calculation that is made. And we figure out which are the important words for a given. For example, if chasing is there, right, then we should focus on criminal and FBI as the other important words, and right, and less on other words in the whole sentence, right? So that is made possible, right, by the attention calculation that is made, which is what is shown here, right? So the what happens is every word kind of outputs those three things, right? The query, key, and value. And then we do a computation of q, k, and v. The attention is calculated for each word using this kind of a softmax function, which is q, k transpose, and then it's normalized by a division, which is dk is a dimension number, and then you take a multiplication over the values to get the attention score. And essentially what this gives is for every word, it tells which are the important words, other important words in that sentence. And similarly, right, for images we will see, right, for a patch of an image we'll see which are the other important patches that need to be that are related, and that need to be paid attention to for this given patch. So it's pretty similar, right? And yeah, the same is kind of captured, right, more mathematically in this slide, where you see that for example, attention matrix, which is the typical attention matrix that is formed, and that comprises of the qk dot products, right, at each step of this whole matrix, right? And then which then you do a softmax, right, of this dot product, as we saw here, right, which is the qk transpose, the dot product is done, and then do the division over the root of dimension. And then you see that there's a multiplication, right, of the values as well, so which is exactly what we saw here as well, right? The multiplication over v, and then the output is formed. So every word you essentially will the word will output q, k, and v, right? And then you do these operations, right, to calculate the attention score, right, for every other word compared to this. And so see, the key points to note here are that the complexity, right, is order of n squared. This matrix, as you can see, right, is a n by n matrix. So naturally, right, the complexity of the attention operation is O of n square, where n is the sequence length, right? Of course, sequence length as in number of words in the input in the case of NLP, or it becomes number of patches in the case of a vision world, right? So as we will see, the again, right, more deeply into the multi-headed self-attention networks, which form the basis of transformers, right? So the MHSA, as they are called, right, multi-headed self-attention, comprises of two broad things, right? One is the encoder and the decoder. See, basically, encoder helps the forms some kind of an embedding, right, for the input, and then so that output, right, output of the encoder is sent to the decoders. So decoders essentially try and figure out how important the given words are, or the set of words are to a given word, and they have access to the whole input in an encoded form, right? from the encoders. And of course, you need to have all the normalization and all other operations as well in that process, right? We did see the normalization operation, which is a division operation, right? So you had some of that, you have a normalization layer and all of that will be there. And then, of course, you had the, for example, again, the linear layer at the end form, which is a fully connected layer, and then a softmax layer, right, which will actually be the classifier, right? So you see that this is the transformer layer as it's typically called, and you have several such layers in a typical transformer. You could have 12 layers or more, and they form the basis for example, it could be image categorization or classification, right? And then we will move quickly into the vision transformers. So what we had seen so far is the transformers, but in an NLP setting, right? And so the Google paper, which was the 2017 paper, right, which is cited here, right? Attention is all you need, also worked in the NLP context. So the first paper to kind of adapt the transformers to a vision world, the world of computer vision, is the 2020 paper cited here, which is an image is worth 16 by 16 words. And so this paper is the seminal work, right, which is known as the vision transformer, or famously called VIT. Now the here the key thing is, what they do is to split the image into a set of patches. So you have the whole image, right? You can see here how it's split into 9 patches, right? Or it could be more depending on the how many patches you want, and what's the patch size versus image size and all of that. So you form a series of patches. So that's what is being given here, right? You have a linear projection of the flattened patches, but you have to have a position. See, one of the key things in a transformer is that it loses the positional information, right? So unless there is a positional embedding which takes care of the position of the patch, right, with respect to the overall input, right, you will lose that positional information. So essentially, right, you will, for example, in a sentence, the order will not matter, and the transformer will simply look at words which are all related to this particular word, and it will not really look at the order of words, right, in a sentence, unless we explicitly take care of position embedding. So that's what is done at this layer, right, where the positional embedding is given along with the linear projection of the flattened patches, and then this is sent to the encoder. So if you had seen the transformer architecture, right, they had encoder and decoder, but in the vision transformer there are no decoders. So that's the difference, right? The essential difference is it is just the encoder part of the NLP transformers that are functioning, right, for vision. And of course, you do have the normalization and the fully connected layer. That's what is known as an MLP layer, which is a multi-layer perceptron here, and which actually forms the classification layer, right, which is this layer. But you had the decoder and other things, right, for NLP, and especially for translation and all that, right? None of that are there for the vision world. So you just have the encoder layer, and then followed by the MLP layer. That will be the core architecture for the VIT, the vision transformer. And this helps in image classification. And they were able to show that this was an ICLR 2021 paper that they were able to get significant performance compared to a lot of the CNNs, the convolutional nets, on the transformer. So transformer was able to perform as good as CNNs, and I think in some cases it even outperformed the convnets. So this was a seminal paper, right, in the field of computer vision. And but of course, the one issue is still that the complexity is still O of n square, complexity with respect to number of patches. So if you see the original vision transformer work, it kind of split into number of patches, right? So depending on that number, so n is the number of patches, your complexity is still O of n square. So which was what was the problem? And of course, the other issue was also that because the number of patches are limited, so you tend to not get very high resolution images. So the low resolution output is what you typically get from the vision transformer. So this became couple of these challenges were there. So the subsequent work, right, since 21, right, since the VIT paper has always been to get efficient vision transformers, right? So to overcome the order of n square limitation, and what can we do to do that to improve the efficiency of transformers, vision transformers, so that two things. One is they can be used more efficiently, right? They require less training, less computational resources for training. Also, they can be applied on possibly dense prediction tasks. See, because the VIT was not able to handle dense input images, right? It could handle only low resolution images, right? So it could not be used on dense prediction tasks, whereas it was okay on coarse classification tasks, but the segmentation, or the semantic segmentation, or other computer vision tasks which require dense prediction and require you to handle fine-grained information, that is little harder for the vision transformers. So the subsequent work focused on making transformers efficient as well as applicable to dense prediction tasks. So you see two representative transformers which I have given in this slide. One is known as the pyramid vision transformer, or PVT, right, which is the seminal paper. So there see, one main advantage was the compared to the traditional VIT, you could now deal with fine-grained patches, whereas the VIT used to have only coarse-grained patches. And they had this notion of progressive shrinking pyramids. So the pyramid architecture, where the size of the patches keeps becoming different, right, from each layer, and which results in being able to handle significant high number of patches, right? Fine grained patches can be handled because of the shrinking pyramids. And of course they had a special attention network as well. See, we keep saying, right, the complexity of the attention is O of n square, whereas this was a spatial reduction attention operation that they performed, and which had a slightly lesser complexity compared to the traditional O of n square attention complexity. And so this one was a seminal work known as the PVT, right? And then the other work was known as Swin Transformer, see, which again was a seminal work where so they had the notion of shifted windows, of attention nets between the layers. See, in the traditional VIT, across layers, the attention window remains the same, whereas in the case of the Swin Transformer, you see that the shifted windows are there. So, for example, layer 1, if you had these kind of attention windows, right? Layer 2, there is layer L and layer L plus 1, the windows are quite different. So what happens is the kind of information that is shared and across those layers becomes quite different, and you're able to take care of long range dependencies between the patches, which was becoming difficult because your window was localized and it was becoming harder to take care of image relations across windows. Whereas because this is a shifting window, right, you were able to handle that much better. Sorry. So that was the couple of representative transformers we saw, which were able to make the vision transformers perform well, perform efficiently. Also, which means they required much lesser computational resources, or flops in the number of floating point operations was much lesser, and they were also able to apply these transformers to dense prediction downstream tasks like semantic segmentation or object detection. So that was why these were seminal works in the space. And of course, we will now go to the essence of the spectral transformers as well. See, one of the challenges we saw, right, is the computational complexity. Also, right, the other challenge was that it was becoming harder because of the attention operation getting localized, right, because of the windows that we saw, right, to handle global information, and also the fine-grained information in images, right, became harder to handle. So the GFNet was proposed, which was handling. So what they were doing was, in essence, they used see the relations between the patches. Instead of computing in the original image space, they computed the relation in the Fourier space. So they took it to the frequency domain and computed the relation between the images, right, in the Fourier space, and then do an inverse Fourier transform. So they had a fast Fourier transform layer, and then they did as you can see here, right, a multiplication operation, right, which is term by term multiplication, right, on the frequency domain features with the what are called as learnable global filters. So once you do this, and then you did an inverse transform, right? So this was one whole layer, whereas this three-step layer replaced the entire attention layer of transformers. So they took the the typical VIT, the vision transformer, and completely replaced the attention mechanism with the three-step process. So the 2D fast Fourier transform, this term by term multiplication is the second part of it, which is the frequency domain features multiplied with the learnable global filters weights, and finally the inverse Fourier transform, right? So these three replace the attention mechanism. Now what this means is, in essence, that the complexity completely changed. It became O of n log n instead of O of n square. And that is significant, because then you're able to get same performance but at much lesser complexity in terms of computational complexity as well as memory complexity, right? Both reduced drastically, and they were able to show that, right, the GFNet was able to perform on par with VITs, but at much lesser, for example, number of parameters was much lesser compared to the traditional VIT. And of course, there were a couple of other efforts which are recent papers, and one is known as the wave VIT. See, instead of using a Fourier transform and looking at only the frequency domain, see, one of the challenges there is that the still, right, the you are missing out on the time domain completely, because it takes you only to the frequency domain, whereas the wave VIT, as it's called, right, they were able to use the what's known as a wavelet transform, which was the DWT, the discrete wavelet transform, instead of the Fourier transform, right? So now this one, the essential difference is that the this is having both the see, instead of just taking it to the Fourier domain, you're able to do both Fourier and time domain in the DW, the wavelet transform. So that results in being able to handle fine-grained information, right, across the Fourier and time domain, and which helped them to achieve better performance than almost all other vision transformers. So Wave VIT is the state of art, right, for vision transformers, which is only bettered by our work, which we will see right in the next few slides. And of course, you also had the Hilo attention paper, which was also one of the few spectral vision transformers. Here, what they do is they kind of explicitly split the image into the high frequency attention and the low frequency attention layers. This they do in the uh, the input gets split, right? In the channel itself. So then you are able to get to the high frequency attention and the low frequency attention. See, the main advantage being that see certain the high frequency layer gives certain kinds of information, whereas the low frequency information is different. So by handling both separately, they're able to get the best of both high frequency information and low frequency information, which then results in significant improvement in performance, right? Now, this was the Hilo attention. And of course, we have a comprehensive survey of different transformers known as efficiency 360, but which I will not get into details of. We don't have time for that today. But we'll quickly go into the scattering vision transformer, right, which was our NeurIPS paper, right, 23 NeurIPS paper. So we'll quickly go into that. See, what we have done is to essentially, right, get to this the because we classify the input into the top five predefined categories, and by our scattering vision transformer, but we have to make it efficient in terms of parameters, computation. Also feature representation needs to be robust. So see, essentially one of the issues, right, in the vision transformer, as we have seen, right, is the quadratic complexity of the vision transformer with respect to the sequence length. And typically, right, many efforts like we saw, right, the PVT and whatnot, right, they all have some way of downsampling operations, right, some kind of downsampling operations over the keys or values to reduce the computational cost. It could be average pooling, or it could be different ways of downsampling. But the issue is all of those downsampling operations are not invertible. So this can result in information loss. So this is one of the key things that our scattering vision transformer addresses and results in, like we saw, right, the good performance with lesser complexity. So complexity could be in terms of memory, so the number of parameters, computation cost, right, which is in terms of G flops, and latency. So latency becomes the, for example, it could be in terms of inference time, right? So all of these three dimensions we take care of in our work. And essentially, right, the issue is to be able to capture fine-grained information in the images effectively. This was what was lacking in many of the other spectral transformers that we saw, right? So we came up with the scattering vision transformation, the SVT as we call it, right? Here the see, as you saw in one of the previous works, right? They were using a discrete wavelet transform, right? But instead of that, see, we use the what's known as a dual tree complex wavelet transform. So now this is quite different from the DWT as you call it, right? And so this results in actually being able to split the image into the fine grained and the low frequency and the high frequency components. And this becomes an important aspect because so that is able to handle both fine grain and coarse grain information, right, in the images, resulting in significant improvement in performance. So the key, so the three key aspects, right, of our work The first is the DTCWT transformation, which is the dual tree complex wavelet transform. So we use this transform in the initial layers of the transformer, right? See, the deeper layers still have attention nets, right? But the initial layers have the DTCWT transform. And then we have a special gating network, which spectral gating network, which comprises of two mechanisms, which is the tensor blending method and the Einstein blending method. So we'll see quickly, right, how these two methods help in the gating network. And then we have a new mechanism for channel and token mixing, right, which is the contribution that we made, right, to the field. So if you see this, right, it just kind of rewords the contribution that we have made. So which is the first time the dual tree complex wavelet transform was introduced into vision transformers. And it helps in decomposing the image features, right, into low frequency and high frequency features. And then we had a spectral gating network, which uses the tensor blending mechanism on low frequency components and the Einstein blending mechanism on high frequency components. And then we had a efficient way of mixing, channel and token mixing, right, with the help of Einstein multiplication. And then you will see that we have shown that by a lot of significant performance studies that SVT beats all transformers, right, in performance in terms of image classification, as well as on some downstream tasks like instant segmentation and so on. So we'll see some of that quickly. So this forms, I know I have to wind up. Maybe I'll take a quick 5-minute view and give you an essence of the scattering vision transformer, our NeurIPS work. So see, this comprises of the two methods, right? Like I said, right, the TBM and the EBM, which is the tensor blending and the Einstein blending methods in the initial layers, right? See, the scatter layer, as we call it, right? So there are alpha scatter layers and L minus alpha attention layers. Like I said, right, the deeper layers are still attention layers, but the initial layers are all scatter layers. So see, the essence is that the attention layers still take care of long range dependencies between the image patches and so on, but the scatter layer takes care of localized information, which is the fine grained information available in images. So because of these two, we are able to combine the scattering layers with attention layers. We are able to get the best of your fine grained and coarse grained information and resulting in significant improvement in performance. We also use a hierarchical architecture. We saw the PVT, right? That also use a hierarchical layer, right? So this is also a hierarchical architecture. So the final architecture will be in this form, where there are a number of stages, right? And each stage having some number of scatter layers and attention layers. So this is how the overall architecture comes out. And then of course you have some detailed view of the same. The one key property is that the DTCWT transform, the dual tree complex wavelet transform that we are using, right, is fully invertible. So which means that there is no information loss when we do the inverse scattering transformation and go back to the original image space, right, from the feature space. So that there's no loss of information. Whereas we saw that some of the other transforms can lead to loss of information. So that is one important difference that we should understand. And of course, by combining the Einstein blending method, right, with the tensor blending method, we are able to have a tonal and token and channel mixing mechanism, right, which helps. So in the interest of time, I'll quickly talk about the data that we are using and how quickly we can get to the performance study. So see, the ImageNet data is well known, right? You have close to 50,000 images on the test set. And of course, training set is beyond 1 million images. And then you had so we built the ImageNet, so the scattering vision transformer was built on ImageNet data and then fine-tuned on other data sets. For example, CIFAR 10 or CIFAR 100 training set, and then used for, so transfer learning was applied, and we have used it on other data sets like CIFAR or flower data set or car data set. So you see that some of these are like very highly specialized data sets, and where you will see that our SVT performs well on these data sets as well. So you will see that we made detailed comparisons of the performance of SVT compared to a host of other transformers. So we see the ResNets are the basic convolutional net based deep nets. So they are not transformers, but all of the others here are transformers in some way, right? The LIT V2 is the hilo attention that we saw, right? And we've seen wave VIT as well, right? So wave VIT and LIT V2 form the state of art before, of course, our SVT. So SVT beats all of them. So you see that the performance of SVT, even the small, the HS as we call it, right, is the small one, and the base architecture is the HB as we call it, and then the large one is the HL, and it goes up to 97.5 or 85.7 top one accuracy on ImageNet dataset, which is the best performing transformer as of today. And then you will see that compared to, for example, GFNet, which we saw, right, or other spectral transforms, right, ours SVT kind of outperforms all of them. And compared to other hierarchical transformers like your wave VIT or PVT and all of them, right, it outperforms all of them as well. And in terms of see, what we will do is not go into too much details on the performance studies, but then what we have done is to essentially do different ablation analysis. And so I'll make the slide deck available, but you will see that, for example, even on transfer learning, right, where we train it on ImageNet dataset, but fine tune it on other data sets and test performance on other data sets like CIFAR or flower or car data set, right? So SVT outperforms all competing transformers, as you can see here, right? Similarly, right, even on other tasks, like even, for example, the downstream tasks such as instant segmentation task, right, where your mask RCNN is the backbone method. So even here, you can see that the SVT outperforms other transformers. So as well as your CNN based architectures, right? Your ResNet is the CNN based architecture. And of course, the kind of characterization, right? It kind of shows that the low frequency filter coefficient, how it captures the shape with the maximum energy part of the image, right? See, what we have seen is the in real life, right, the application of SVT has been in extreme classification, right, where you have fine grained classification, right? The number of classes are very high, and you need to be able to perform fine grained classification. There, SVT outperforms all competing transformers to a great extent. So this is one business use case. We are seeing the use of this in certain retail customers and their cases and all that, right? So we are working, we are in a proof of concept with a large customer of Microsoft, and where we have shown that the extreme classification use cases can benefit a lot with our spectral transformers, right, our SVT. And we are also applying it in medical imaging, right, where you have the MRI scans and CT scans and all that, right? So we are looking at, for example, the fast MRI data set, and initial results are promising. And because of its ability to handle high resolution data, we are seeing that again on satellite images, right, which are high resolution images, the scattering vision transformer might perform well. We are still exploring that those applications. And I had just one last slide right before I close, because I'm talking to a lot of people in academia. I want to give future directions, right, where um, people can take the work and can start off from here and start exploring the research directions, and see, each of these could potentially result in a NeurIPS kind of paper, right, if explored. And you get a good idea for these, right, could get a NeurIPS kind of paper in each of these areas. So, for example, in the spectral transformers, right, efficiency is still an issue, and various ways of improving the parameter efficiency may be there, right, including, for example, the exploration of knowledge distillation or low rank factorization. See, in some sense, our work is a low rank factorization where, for example, the agent values only need to be looked at instead of having to look at the whole matrix, but you can just look at the agent values. And of course, there are ways of looking at the computational efficiency, how to maximize the computational efficiency, right? For example, using mixed precision training and or quantization or pruning techniques. So these could result in significant gains in computational efficiency. And of course, the in terms of sorry, it's G flops optimization. Sorry, not G lops, but G flops optimization, where you can look at distributed training, right, across multiple GPU nodes. Right now, we are using single GPU node for training, but yeah, you can distribute the training. See, the other important research directions include, being able to handle privacy and bias issues in transformers. For example, either using differential privacy techniques or federated learning techniques, and to develop methods for detecting and mitigating biases in the transformer models, right, especially in language and image domains. So that's something, that's a hot area of research, and we can look at that. The last one is, of course, in terms of efficient transformers. Again, you have some of the recent notions of approximation transformers, where you can instead of implementing the complete attention mechanism, which is order of n square complexity, you approximate it, and have approximation techniques which will help you to achieve efficiency, right? Of course, the trade-off between efficiency loss versus accuracy becomes important. But yeah, so that's the trade-off that we can explore. The other thing is, see, the transformers become the basis, as many of you may be aware, right, of the LLMs, the large language models, and your GPTs and all that, right? What is T in GPT, right? It's a transformer. It's a pre-trained transformer that is used as the basis for many of these large language models. So when it comes to fine tuning of these large language models, right, that is where we feel there are techniques which could help, and which could be explored, which will help in adapting these pre-trained models to specific tasks with minimal computation overhead. See, right now what's happening is, each task you have to kind of fine tune the transformer, the LLM, for a specific task. But once you start looking at performance across tasks, then they become this becomes a big challenge. So that's where your if you're able to come up with mechanisms which allow you to adapt the pre-trained models and help you fine tune it across a set of tasks, then it might be significant benefits may be obtainable. So essentially, right, we have seen that the um, uh, the spectral vision transformers, starting from the computer vision field, starting from computational the convolutional nets, all the way to transformers, vision transformers, as well as we have seen how they perform, and how vision transformers could be implemented, as well as how we can implement the SVT, right, as we saw that. So I'll pause here and see if people have questions, and over to you, Mudit, for questions.
Thanks, Vijay. There are actually a lot of questions. I've added them here. Let's pick them one by one. The first one is around using this in the context of multimodality, and because our bootcamp was probably is centered around LLMs, maybe that this is maybe why this has come up. How does the labeling of data for fine-tuning LLMs, multimodal LLMs, and vision transformers work? This is asked by Suraj.
Sorry, I was just taking a medicine. Sorry. What is that?
Yeah.
What is the question? Can you rephrase that?
How does let's say one has to fine-tune a data set for one has to prepare a data set, label a data set for fine-tuning multimodal LLMs or vision transformers. So is it similar to the traditional labeling techniques, or there's something else that is used in that case?
See the labeling. So what you're asking is for multimodal LLM. See, yeah, there are a set of recent data sets that have come up for multimodal LLMs, and which are quite different. So I can put you across, or I can send you a list of these data sets which can be used for multimodal LLMs as compared to traditional data sets. So traditional data sets may not work as such. So you have to have some mechanisms to handle those. And so yeah, the multimodal LLMs, it's not trivial, right? Because across modalities, for example, you have text data where you will have lot of text data sets which are all labeled only for text, and you'll have text classification labels and all that, right? Or you have images where you have image classification labels and all. But then what you may need is, given an image, a description of the image, right? So that kind of data set is what you need. And there are some data sets which are available, especially in the recent past, they have become available, and which help in training a multimodal LLM, in this kind of fashion. Like I said, right, where you have an image, and then you have a corresponding description of an image. So that's the label you need, right? Goes across modalities, right? So that's the kind of data set you need. So your traditional data sets may not be um, reusable as is in a multimodal context. I hope that answered the question. Are there other questions? I'm not able to see the questions. Mudit.
So it is not syncing up with YouTube directly, so I've added
Oh,
within
okay, got it. Yeah.
banners feature of StreamYard, so I can see it for that reason.
No worries, no
Um,
worries. You can let
so
me
you can
know.
see it in the bottom as I display them. The next question, because it's on a similar line, I'll pick it. It's around RAG itself, RAG and LLM architectures that typically use vector index retrievers, and then so they can they be simply used with vision transformers as well, or there is some changes that is needed to be done in that case?
I think that's a great question. I think this is one of the things we are also trying to investigate. See, because the RAG architecture, right, has been typically used in the NLP context. So they have not been applied in the vision transformers yet, and it's not clear, right, whether it could result in significant improvement in performance or not. So this is still to be explored, and I may not have a definitive answer on this, but yes, this is a great area to explore, and open research questions are there, so we can look at those. Yeah.
Okay. Thanks for answering that. Then the next question is very much specific to spec transformers. So it's basically spec transformers and PVT. So how do spectral and attention layers in spec former work compared to PVT's multi-scale approach?
See the pyramid vision transformer. Maybe I can quickly go to the architecture of that compared to this. I had one diagram I thought for PVT. Yeah, see the thing is, the essential difference, right, is that the see, the PVT had see the hierarchical architecture is the same. So even we have a typical, hierarchical architecture. So it's not much different. But the see, the attention layer itself is quite different. See in okay, for example, how that will be different, right? And I'll come to this. See, in the PVT, what would happen is each layer, right, will have all attention. There will not be any scatter layer here in PVT, right? Whereas we have a scattering layer. So what happens is the early layers for us, there are alpha scattering layers compared to PVT. PVT will have all attention. Whereas if you look at GFNet, GFNet has all spectral layers. So these three broad categories. So your PVT has all attention layers, your GFNet has all spectral layers, whereas we have our SVT has mixture of scattering layers and attention layer. See, the key difference is, see, this helps in handling the scatter layers are able to handle the fine grained information available in the images. Attention layers typically handle long range dependencies. So by combining these two, right, we are able to do both fine grained information, which is the local information, right, available where possibly patches near each other are related and all that, right? That is done by the scattering layer. But attention layer takes care of across, uh, across regions of the image, right? Long range dependencies, right, or taken care of by that. So overall, what this means is the compared to PVT, our performance is significantly better. So for instance, you can see, I will show, I'm just seeing if PVT is here or not, but if it is not, see, PVT V2 is here, and you can see, for example, that it goes up to 83.2 top one accuracy, whereas ours goes up to 85.2. So 2% improvement compared to PVT is what we are able to achieve at probably the same complexity level. See, the complexity level is actually lesser. So because if you see, PVT has 45.2 million parameters, whereas we have only 32 million parameters. And at that, so with respect to number of parameters also, we are lesser, but we are also have a 2% improvement compared to PVT. So, and this is possible primarily because of the initial scattering layers that we introduce, whereas PVT is all attention. I hope this difference was clear, right? Mudit, back to you.
Yeah, thanks for that elaborate answer. Actually, there are a few more questions, so depending on your bandwidth, we can pick them up.
Maybe I have 5 minutes and then 7 minutes, maybe till 6:15 I'll stay on.
Fair enough. So let us pick two questions which are quite common. First one is, which is asked by many questions. It is asked right now live by Ayush, who's a student at IIT Guwahati. As a fresher, where can I go about studying these concepts?
Yeah, I think that's good because see, the key is, right, the lot of citations are actually given in the slide deck itself. This is what even Mudit was talking about initially, right? I have given several links. See, in every slide, I have given the citation to the paper or the link from where I have taken some of these concepts. So, for example, some diagrams are taken from those places. So, I've given the citation. So, every page will have a citation. So, the key is to just go through all the citations that I have given, and then those citations and the sites, the websites that I've linked. I think those form the basis for all of these concepts that you are seeing, right? Including attention, the wavelet transform. All of those links are all given, right, in my slides only. So if you go through all the links, you will get a strong idea of all of these concepts and all. So you will do that.
Okay.
So yeah,
Thanks.
Mudit, the slide deck I can make available so that you can share it across to a larger group.
Yeah, that is splendid. So what we'll do is the ones who are watching live, and if you're watching it later on, we'll update this on the description on YouTube and other platforms. On LinkedIn, we'll put a comment maybe, so you can go and check there. And there is one question specific to RAG and one question specific to SVT.
And Mudit, I am seeing one question here. So I think in this comment, one question came up. So maybe I'll answer
Yeah.
that first.
Yeah.
Because it says, see, in for example, an engine defect detection use case, how to decide whether to use PVT or SVT, right? Um, See, it should depend on simple thing, right? If it is a fine-grained, classification kind of a problem, then SVT is expected to outperform PVT, right? So in the case of engine defect detection, is the what's the resolution of the images, and is it fine-grained images are important, and you need to be able to classify fine-grained images, then it's likely that SVT will outperform PVT. And one simple thing to do is test out both, and get back to us. If you think SVT is not performing well, then we can see why, and we can do something about it. But otherwise, if you're getting an improved performance, well and good. So feel free to test out both. But my reading is that, especially for fine-grained information and fine-grained classification, SVT will perform better than most other transformers out there.
Okay. Thanks, Vijay. The last question is pretty short. Actually, it's slightly long one, but I'll summarize it. Basically, they're asking if, since you didn't mention, you said that it doesn't use a decoder. So can SpectFormer be integrated with other modalities like audio and all? And is it similar to a Flamingo's approach, which uses a separate image and text decoder generally?
I haven't seen Flamingo's architecture, so I may not be able to answer that. But the thing is, um, yeah, see the. Can you kind of go back to that question, Mudit, again,
Sure.
just to refresh? Okay. So the other modalities. Okay, got it. Yeah. So yeah, see, this is something we are working on. See, applying, the scattering vision transformer to other modalities. See, we feel that it will perform well even on audio datasets. See, the main thing is audio datasets also have the frequency information and all that, right? So in that case, we expect good performance on audio datasets, but we have not actually taken an audio dataset and experimented with it. So I may not be able to give you a comprehensive answer there. But see, any dataset where frequency information is there, and the spectral dataset kind of thing, right? Then SVT is we expect SVT to perform well. So that's the honest answer, because we have not had the time to look at any other data sets like audio or NLP yet. We are applying it to NLP because see what we are doing is, instead of the DTCWT transform, the dual tree complex wavelet transform, we are using a different transform there to make it applicable in NLP context. So we will this is a paper that has been communicated, so I may not be able to share too much details of that, but we have tried it out on an NLP context by changing that transform. Instead of using DTCWT, we use a different transform there, and which we feel is better applicable in an NLP context. I hope that
Okay.
answered this question, right?
Yeah, that does pretty much. So with that, we're almost towards the end of the question, in fact.
Fantastic.
Thank you so much, Vijay. And a quick note for attendees. So if you're watching this on LinkedIn particularly, you can find Vijay's profile on the speakers tab. On LinkedIn, we'll put his profiles link. So you can go ahead and follow him. So when he publishes any paper or anything on those lines, you can go and check it out. You can also check out the work of Microsoft and his team. And Vijay, thanks a ton for being on this particular session. I know it's stretched by a bit of time, and you were very kind enough to look at all the questions and answer them. So thanks a ton for being on the session. Really appreciate it.
Absolutely, Mudit. My pleasure. It was great talking to you guys. Yeah.
Thank you everyone, and we are looking forward to seeing you towards the end of the boot camp. Cheers, bye.
All right.